Welcome to The Explainer. Today, we're diving straight into a completely mind-bending reimagining of character encoding. We are stepping way back from standard software bloat and arbitrary memory heaps, and we're heading directly into the realm of pure mechanical geometry, all driven by something called a 4D control tensor. I really want you to reconsider everything you know about basic computing memory, because the source material we're exploring today asks a pretty radical question. What if the characters you type every single day aren't just a flat list, but actually act as physical graduations on a hyper-complex slide rule? It's a fascinating paradigm shift, and we're going to break down exactly how it works. To unpack all this, we'll follow a clear path. First, rethinking the ASCII table. 2, the space character fulcrum. 3, our main focus for today, ASCII's 4D control tensor. 4, the circular slide rule. And finally, a mechanical computing engine. All right, Section 1, rethinking the ASCII table, from flat text to geometric manifold. You know, standard computer science really trains us to look at ASCII as just a flat grid for text parsing, basically building these massive, tangled logic trees just to figure out what a string of text means. But as this comparison lays out, this new architecture replaces all that messy lexical scanning with the unyielding laws of physical, bitwise rotation. Instead of reading a string of text, this architecture treats the character grid itself as a hardware-level machine. The physical alignment of the bits is the calculation. Moving to Section 2, the space character fulcrum, the hinge of space. So to build this mechanical engine, we first have to find its center of gravity. And surprisingly enough, it sits right at 0x20. Yep, the everyday spacebar. But here it acts as a literal dimensional bridge. Everything below it, from 0x00 to 0x1f, is hidden machine logic. And everything above it, that's your visible data. By making the space character the hinge, we get this perfect launch pad pushing data out into the visible universe. You have an absolute floor down at 0x00 and a ceiling up at 0x80 that acts as a hard boundary, forcing the projection outward. Section 3, ASCII's 4D control tensor, the core hardware-level clutch. Now let's really zoom in on the exact sequence leading up to that spacebar fulcrum, because this right here is the true focus of our explainer today. Notice how the hexadecimal values 1C through 1F aren't just random commands. They actually act as a strictly ordered four-dimensional funnel. They step down dimension by dimension, from file to group to record and right down to unit, structuring the data's geometry before it ever even hits the printable space. You can think of this sequence kind of like a hardware-level clutch in a manual car. Step 1. The escape character basically disengages the engine from linear processing. Step 2. It shifts gears, funneling flawlessly down through that 4D tensor hierarchy we just looked at. In step 3, boom, the transmission re-engages exactly at the space character fulcrum. It's just a perfectly enclosed execution band guiding the machine state. Now, right within that clutch, there's a crucial balancing point called the lambda pivot. If you look at the 5-byte sequence from 1B to 1F, the group separator, 0x1d, sits dead center. It essentially acts as a structural mirror, kind of like the fulcrum of a seesaw, with 2 elements on its left and 2 on its right, perfectly balancing the entire geometrical frame. Okay, Section 4, the circular slide rule, rotating data geometry. Taking those vectors off a flat grid and wrapping them onto a physical, rotating wheel just changes everything. Data states don't change through conditional loops anymore. They change by physically rotating geometric tracks until they align with fixed cursors. And here is why this is absolutely massive for security. If a memory location is rotated away from the active cursor, it is mechanically impossible to access. It isn't just hidden by software. It is brilliantly, physically secure by design. The source material brings in a concept called a phanoplane. Now, I know that sounds like some really intense mathematical jargon, but it basically acts as a structural building inspector. Because the memory rows utilize exactly 7 elements, spinning the slide rule 7 steps guarantees a closed geometric loop. The machine inherently knows the logic is sound, simply because the geometry physically clicks shut. And finally, Section 5, a mechanical computing engine, the 256-bit bitmapped finite state machine. So how exactly does all this abstract theory become actual implementable hardware logic? Well, by mapping it into polyhedrons. Every 16-white row splits into an outer active shell, a triachous tetrahedron, try saying that 3 times fast, and that wraps around an unyielding tetrahedral core. The beauty of this is when the system reads past the outer shell, it just naturally falls right into the core, triggering an execution switch purely through geometry. Literally no if-then code required. This whole thing validates via a lightning-fast, hardware-level bitwise equation. If it cancels out to 0x1e, which you might remember is the record separator from our 40 control tensor earlier, the state change is instantly accepted. If the bits don't align perfectly to 0x1e, the wheel has misaligned and the transaction is just mechanically discarded. Zero heavy background processing needed. Just take a look at this staggering number. Over 18 quintillion. That is the exact amount of unique logic combinations, seamlessly compressed into a single 64-bit hardware integer, using the 6-axis wheel. I mean, an entire multivariable truth table is evaluated in a single CPU cycle, all via a simple bitwise shift. Bypassing decades of fragile software bloat to return to pure, deterministic geometric machines, it solves some truly massive problems in both efficiency and security. It leaves us with an incredibly compelling blueprint for the next evolution of computation. The math is sound, the geometry is physically secure, so it really makes you ask, are we ready to start rotating the wheel?